Hi everyone, welcome back, and while you're here, hit the subscribe button right now. In this video, I am going to talk about how you can use your own images and masks to train a StarDist model for instance segmentation. In other words, for object segmentation. Why did I put quotes around instance? Because oftentimes you think I'm talking about Mask-RCNN or something else, even though the end result here is going to be exactly the same. The only restriction here is the objects that you can segment need to be star convex, which means there must be a point inside your object where you can sit and look at every direction and find every part of the boundary of that object. If there are any hidden regions, for example, if there are bends and curves and you're sitting here and you cannot see that, then this approach does not work. And why? Go ahead and read the paper, watch my previous video on this specific topic for a little bit more explanation on what StarDist based segmentation basically means. Okay, so here I am going to use the classic mitochondria dataset. I say classic because I have used this in many other videos, and this can be easily, I'll leave the link to this dataset. You can get this from just a simple Google search, just EPFL mitochondria dataset. You should be fine finding that. Otherwise, I'll put the link to the dataset down in the description anyway. And we are going to use these images and the masks that came along with these to train a StarDist model and then also to predict. That's the goal for this video. So let's go ahead and jump in. And I just did EPFL mitochondria dataset in case you want this faster. And the first link, let's go ahead and click on it. It's a bit slow. There you go. So this is the image data set. They have the mask, what they call the test data set, and it also comes with the corresponding labeled masks. So I downloaded this. It's about 165 images and of size 700 by something. I don't think they're all 1065, but whatever the size was, I divided them into 256 by 256 patches so I can actually do the training. And that's exactly what I have as part of my Mito dataset. You see my Mito images. They are 256 by 256 images. And if I go back and look at the Mito masks, I crop the masks obviously exactly the same way. So I have mask 1577 here. And if I go back, the second image, 1577, you see these two mitochondria right there. So this is the data set I'm working with, and with that information, let's go ahead and open our Colab notebook. Why Colab? Because you can do it on your side too. If I do it on my own IDE, then maybe the installation of StarDist or something, you never know what issues you may run into. So I chose to do it in Colab for this series of videos. Okay, so first thing first, the runtime is connected. I enabled my GPU to change runtime. I think, yeah, there you go. And let's go ahead and pip install StarDist. This is how we always start. Once that gets installed, let's go ahead and load our libraries. This process is pretty straightforward, actually. Let's import all our libraries. This is NumPy, Matplotlib, and PyPlot from Matplotlib, and glob to go through our directories to forget the file names, and tqdm so we can see the progress when we are going through certain loops, and so on. And from StarDist, I am going to import certain useful functions like fill holes in the labels if you want to do that. And random label CMap is just when you do this color map, how do you want to label them? Like it can be random colors. So some of the little things, and we'll go through line by line so you get an idea of where these things actually fit in. Once the libraries are imported, first thing first, let's set a random seed for my label CMap, just random with that seed. Obviously, watch my video on random, how random is not random. It requires a seed, and from that seed, it calculates using certain algorithm. And I set my random seed to 42 in this case, which I always set my random to 42 because that is the answer to the life's ultimate question. Okay, so that's the random color map part. And now we need to get our file names for our images and masks. And it's customary to call our images or assign our images to a variable X and masks to a variable Y. So this part is just a glob. It's not actually read input. Read is coming down here. This is actually get a sorted list of our file names, yeah, for X. And this is the sorted list of file names for Y. And next I am going to read each image and assign it to X, each image, each mask, assign it to Y. Okay, and if my image is only 2 dimensions, meaning it's 256 by 256, then the number of channels equals to 1. If it's multiple dimensions, meaning 256 by 256 by 3, because it's an RGB image, then go ahead and read how many ever. So that's exactly what that line is. I think that didn't require any explanation, but you never know. So now it's reading the images, it's reading the masks. How many images and how many masks do I have? I should have known that, but I think I have about, does Google Drive say how many I have? I think I have about 1600 images and 1600 masks. So let me not waste your time. Or is it 500? Sorry, I lied. About about 550 images or so. We'll know that if it's not clear, we can go ahead and print out the size of our array right here. But for some reason, it's taking a little more time to read, and I'm pretending to talk to kill time, as you can tell. But let's wait for this to be done and then continue from here. Okay, so it apparently took 1 minute 9 seconds to read. That's okay. It's reading from the Google Drive. And the next step is to normalize them, right? I mean, these are all 8-bit images, so we need to normalize those. So I am going to define the axis for normalization. For normalize, I think I'm using the SB deep utilities. You can use any other, whatever your preferred way of normalizing, by the way. And here I'm defining 0, 1 because it normalizes channels independently. In our case, we don't have RGB multiple channels, so it doesn't matter. And it's normalizing there. And for Y, like for my masks, I am filling the label holes, although I don't think in this data set there are any holes in the label. Typically it happens if you have like little holes here and there. This can be a useful function to fill. I'm just leaving it over there. Okay, and now that we have our images, now let's go ahead. I guess we have 160. It's not 500 that we have. It's probably because we set like a limit of, okay, let's only read that many. But either way, or maybe sorry, I should have been a bit more prepared. But clearly we have 160 images and corresponding 160 masks. And from those, let's actually get a small fraction of those and assign them to train, fraction of them assigned to test. And I am using the code that I got from the StarDist examples, but you can use any way of splitting your images and masks. So here we are just randomly getting a random state and selecting a certain number of images, like 85% to our training and 15% to our validation. That's exactly what we are doing right there, and summary should be printed out right there. 136 training images and 24 validation. In fact, you can use test train split, I think from scikit image. You can use that to segment, to split your data set. Either way, the goal here is to have your train and test. Okay, nothing new, very similar to how we approach our deep learning in general. Sanity check. I love sanity checks. I am randomly plotting some of the images and corresponding labels to make sure they are actually in the array in the right order. So let's print one. So that makes absolute sense right there. Let's print one more, just in case if this happened by chance. Oh, it's only one. Maybe I'm not randomly looking at the, no, I am randomly looking at the images. Let's see. Oh, I have no clue why it's just showing exactly the same. Please go ahead and change the image number if this keeps happening. Upload image. I don't want to troubleshoot right now. The last time I checked, it was working fine. Let's just do. Okay. Sorry. Let's leave that. I have a habit of just overthinking about things that can be easily fixed after. So this is, at least it tells us that, okay, you have an image and the mask and they're working, they match. Now let's move ahead. And the next step is We can check the configuration document, like to get an idea about all the parameters that can be defined. Like for example, unit depth, like how deep you want your unit to be as part of this architecture. Like StarDist, you can use multiple architectures, but in this case, unit architecture. And then remember, unit is not predicting the masks. It's actually predicting two things. One is these distance maps, and the other one is the probability of something being a center of the object. These are the two things, and for that you need unit and what is the depth of that unit, what is the kernel size, and a whole bunch of things that you can actually define whether you would like to use GPU or not. So all of these. So with that information, let's go down. Number of rays equals to 32. That probably is one of the parameters here, although I did not, yeah, right there. Number of rays is the number of radial directions for the star convex polygon. If you watched my previous video, or if you watch this is the number of rays right there. How many do you want? Okay, so that is something you can input, and number of channels is something we know. Our number of channels is 1 in our image, so we need to provide certain inputs, and that's exactly what we are going to do right here. So first of all, our number of rays equals to 32, the default value that they have used or suggested, and use GPU equals to false. Play with this and predict on subsampled grid. Grid equals to 2 by 2, and our config file, like the config file I just showed you, update that config file by defining our new number of rays and the grid, and use GPU number of channels and so on. Let's go ahead and run this line. Now you can see these are all the updated parameters. What axes do we have? Y, X, C, Y, and X, and number of channels, right? So width, height, and number of channels, or height, width, whatever you want to assign Y to. Height, width, and number of channels. And what type of backbone are we using for our training? Unit, and a grid of size 2 by 2, number of channels is 1. So based on this, it defines its unit and the rest of the experiment. Okay, and weights last is what we will be using as part of our prediction later on. So how many epochs and all of that. We can define some of these later on as part of training. So that is our config file. Now, if we are going to use GPU, then you can set it to limit the GPU memory to 80%. So it leaves 20% for other activities, like recording a video, for example. But in this case, I'm using Colab anyway, so it's not going to affect my local GPU. Okay, so how do we train it? Now that we have our X and Y for training and for our validation, first of all, let's define the model. The way you define the model is StarDist 2D. Remember, we imported StarDist 2D from stardist.models. And from here, let's go ahead and provide the configuration. Conf. Yeah, we defined the conf right there. Let's provide that as an input. And what do you want to name your StarDist model? I'm calling it StarDist tutorial, and this is how it saves in your local drive. Let's go ahead and see. In my drive, where am I saving it? Colab notebooks and models, right? So under Colab notebooks, under models, I have StarDist, because my earlier model that I trained was called StarDist. Now I call this StarDist tutorial, so it will create another folder right there called StarDist tutorial. Okay, so let's close this part and continue. And this is my model. So let's go ahead and define our model. And the next one, define the network field of view. What is the field of view for your network? And it should be larger than the median object size, right? So you have your object size, it should be slightly larger than that. So this one actually automatically calculates that based on our masks that we actually provide. So that's exactly what we are doing right there. So there you go. Let's define that. And also field of view is model.axis title overlap yx in our height and width is the dimension that we are providing here. Again, I'm going through this very fast. You can look at the documentation. If you would like to just use your images and train it, there's nothing to modify here. You can use this template as is and modify your input images and input masks to your own images and masks and try to use this. And there's no reason for me to suspect why it would not work. But anyway, so the median object size that it actually calculated was like 86 and 85 pixels, and network field of view is 94 by 94 is what it defined. Now, let's do some augmentation to our images. And here we are defining a few augmentations. One is random flip and rotation. So it's pretty simple, right? I mean, we are just rotating and randomly flipping, and random intensity changes. We change the intensity randomly a little bit, and then we define our augmenter as it takes your X and Y input image and the mask, both X and Y, and then it does these whatever the operations and returns the new image. So this is our augmentation right here. Again, optional if you don't want to do it. If you have lots of images, fine, go ahead and use your images. And now let's just plot some augmented images. I just picked image number 9. Let's go ahead and plot augmented. So this is how it looks like. This is how the rotation augmented, so you know that it's working. Okay, now it's time for training. Model.train, just like you would with any other Keras based implementation. For example, your X-train and Y-train, and your validation data, xval and yval, and what augmenter would you like to use? What is that function? So our augmenter is this function augmenter. You just saw that, so let's not go back up. And epochs, I trained my model that I'm going to show you later on under predict for 150 epochs. We don't have that type of time right now, so let's just change it to 10 epochs, and let's go ahead and run this just to see how things are getting started. It may look like a lot of things, but basically it's very straightforward. Instead of using your own Keras model, you are just using the StarDist model and defining a configuration file just to let the StarDist model build the right unit for you. And then now you're training a unit, and the unit is not predicting your output masks, because we know that that's probably not that efficient. So it's actually predicting these distance maps and the probability maps for something being at the center of your object. So there you go, it's training, and there's a lot of parameters. You can look at the mean absolute error, and also there should be IOU somewhere. Yeah, IOU metric, and as you can see, the metric is getting better. And in my case, I believe I got like 0.98 or something. Pretty good IOU. Let's go ahead and stop this. We already have a model, and now you can go ahead and do model.optimize thresholds, because by default it has some threshold of 0.5, for example. And when you do optimize threshold, it's going to use your validation data and it's going to optimize that threshold for you. So initial 0.3, it's actually testing a few of these, and it's going to tell you, okay, based on this, the optimized threshold is something, and the details right there. Yeah, so probability threshold is right here. Obviously this is not great. I mean, this doesn't mean anything right now because we haven't trained our model for a long time. So what can we do? Let's go ahead and import my model that I trained for about 150 epochs. So from this point on, let's pretend that we trained for 150 epochs and we are trying to check the model. So let's go ahead and do the prediction, and we know how to do prediction with StarDist. It's model.predict instances, and then you give your images. Okay. And how many tiles do you want to divide this, and go ahead and guess the number of tiles, and play with these parameters right there. But let's go ahead and predict our images. So there are like 24 of them, we know that, and it did all the 24. And let's do the original labels and predictions. This is just plotting. So there's the original label and there's the prediction. Pretty close. It can be better, but pretty close to the original label. So to the point where I'm like, okay, let's go ahead and plot the key metrics. This is great. Actually, I love this because it gives you all the information about precision, recall, accuracy, and all of these for each IOU threshold. Like what threshold do you want to use for IOU? And at some point, probably around 0.5-ish or so is the right threshold where there's a good balance between both sides. So 0.5 is the right threshold right here. Okay, this is training. We're done with training. Let's jump on to our prediction. Now that you have a trained model, how do you segment your images of any size? So let's connect. It's going to yell at me because I can only have one GPU session at a time. So let's terminate the other one that we were just working with, and close and connect. Okay, a few more minutes, I promise. We are getting to the very nice area of reaping the benefits of our training. So Once we get here, it's mounting the Google Drive. Okay, everything is ready. Let us go through the same exercise. Pip install StarDist. On a local drive, obviously you have your own environment. You don't have to do these type of steps all the time. You're all good, but here we have to do that. And I'm going to import the same libraries I already talked about and do exactly the same step. Random seed 6. Let's do 42. Who likes 6? Okay, random seed, it doesn't matter what number. And now let's read our input images that we would like to segment. So these are the ones that I am trying to segment, the Mito images right there. I'm going to show you how to segment a large image, but for now, let's go ahead and import these 256 by 256 images. Our model was trained on 256 by 256 images, so let's go ahead and do that. And first of all, I want to show you that the shape of these images are 256 by 256. So we train the model on 256 and the shape is 256. So, and this part is the same, normalizing your image. And this part is basically showing your image. It's taking a little longer than I thought it would, but yeah, so this part is basically just showing your images right there. Yeah, so these are all the images that we just read. Okay, and our goal is to segment them. It's showing a lot of them. Okay, and my model is going to be the StarDist, right? I mean, this is what we are importing. And where is it importing from? The StarDist library, which the directory which can be found under this path on my system right here. So let us go ahead and define the model. And I am importing rand_int from random, so I can just select a few random images from the list that we actually got and model.predict instances and plot it. So we can validate the accuracy. So it's basically model.predict instances. That's it. Once you have your trained model. So now it's actually predicting on whatever that random image it chooses to pick from these 100 and plus images. This image has no mitochondria, so it's not showing me anything. There is nothing there. So let's do one more. There you go. This one has 3 mitochondria, so it's showing me all these 3 very nicely overlaid on this image. Okay, so it's working great on 256 by 256 images, but what about large images? Okay, so I mean, you can draw polygons again. Because I have this, why not just show it? Yeah, so it's just doing these polygons, and useful if you are publishing a paper to actually talk about how this thing works. Okay, now let's go ahead and load a large image, and these are 756. We'll look at the shape. I think I have 12 images of size 768 by 1024. Obviously not 256 by 256. Normally, when I want to segment these, I divide them into 256 patches, segment, put the patches together into a large image. I don't have to worry about that here. All I need to do is go ahead and normalize it, because we have to. We normalize them, and then model.predict instances on my large image. That's it. I'm not telling that, hey, this is a large image, do something to this. Nothing. I just did this, and it's going to do everything by default in the backend. Crop input images into respective tiles and all that stuff. I don't have to provide, and it predicted, and let's go ahead and plot. That's the beauty of StarDist. How easy is it to predict on large images? Because we don't have to think about it. We have to only think about, what do I want to achieve? I want to segment this large image. What do I need to do that? Go ahead and take my training data, whatever size the training data is, and train a model, and bring the model here and just do model.predict. And this is an amazing output, as you can see, and I can do this on multiple images, and I can actually capture all the details about individual objects. Again, I'll talk about that in the next video and the video after that, but for this, I already think this is a long video, so I should rest my voice, and I should also make sure that you are engaged with these videos, and by not making them too long. If you like them, hit the like button, guys, and also subscribe. Thank you very much.